Hello everyone and welcome back to this next lecture in the DC to DC converter series. In the previous lecture, we had performed an analysis of the flyback converter. So in specific, we had plotted some of the currents, the voltages, and also measured the output. So we more or less understood how the flyback converter works. So with this, we are pretty much done with this converter, though of course there is always more analysis that you can do. However, I would like to stop here and move on to another converter. So before that, let's do a little bit of recap, or rather just lay the foundation for the next converter. So as before I start this lecture, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I do have several full-length courses on the MOOC website Udemy. This is one of the very first courses, which is called Simulating Power Electronic Circuits using Python. And in this course, I talk about the basics, how you can simulate circuits with Python. So for example, there is some background on how to install software, how to install Python Power Electronics, a little bit of basic background of how to simulate basic electrical circuits like resistive circuits and other stuff using Python Power Electronics. And finally, there is a tutorial on how to simulate a buck converter. If you're interested more on the signal processing side, I do have another course which is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can design and implement filters using Python for power engineering applications. So there is a little bit of background about signal processing, about the basics of Laplace transform and discrete time systems. There is finally a case study of how you can implement, analyze, and design a low-pass filter and a notch filter using Python packages such as NumPy and SciPy. The latest course which I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about the basics of how you can model magnetic components using Python Power Electronics. So there is modeling on simulation of an inductor, of coupled inductors, transformers, and finally there is a case study of how to simulate a flyback converter. So the links for these courses are provided in the video of this, or in the description of this video. If you are interested, please do check them out. So coming back to our actual lecture. So let's go and have a little look at our circuit. So in the flyback converter, we have a DC supply. In this case, we've taken a 12-volt source, something like a 12-volt battery, which is connected to the primary of a transformer, right? So these are the connections to the primary of the transformer winding, and this is done through a switch. Actually, it would be in reality through a device like a MOSFET. And at the secondary, we have this 2:1. Actually, we have a 2:1 transformer, though it can be even a step-up transformer like a 1:2 or 1:3 transformer. Anything is possible. And at the secondary of the transformer, we have connected a filter, right? So this filter basically consists of a diode to block any voltages which might be negative, and which will only let through currents in one direction to ensure that this capacitor is charged in a particular direction only, right? And of course, we have this capacitor just to make sure that the output voltage is steady across the load, right? This is a very simple, very simple topology for pretty much any inverter, any converter, right? And of course, we can make some changes. We can, of course, get rid of this inductor because we do have the winding leakage reactance. We can add additional inductance if you want to smoothen out the current, or we can let it go, right? And of course, the final load is just a resistor that is connected across, that is connected across this filter capacitor, right? So this is how the entire system looks, right? This is basically the transformer terminal, and we have inserted the filter between the terminal and the load. So coming back to our simulation. Now, to do a little bit of analysis about it, as we already talked about, in this particular case, the flyback converter has only two windings, the primary winding and the secondary winding. However, in many cases, you can actually have multiple secondary windings, right? So we can, with just one DC supply, serve multiple loads, right? So multiple isolated loads. Now, from a control perspective, only one of these loads can be a regulated output voltage. The others would have to be unregulated. However, in many applications, there is a need only for one regulated output, and the others can, however, be unregulated. So that is still acceptable. So in reality, the transformer that we have, which is currently a simple two-winding transformer, so we have a primary and a secondary, we can have, besides this secondary already there, we can connect additional secondaries as well. And to these additional secondaries, we can connect additional loads, right? So you can have multiple loads served from the same DC supply, and that's one of the biggest advantages of using isolated transformers, right? Isolation transformers. Now, from another perspective, as you might already, as I've already talked about, one of the main concepts of using this flyback converter is that the primary is energized during one cycle when the switch is turned on. It is energized by the DC supply, and when the switch is turned off, only then does the energy stored in the transformer being dissipated to the load, right? So when the primary is being energized by the DC supply, this secondary, even though it produces an induced EMF, it does not supply any current. And the reason for that is because the way we've connected the filter. It is the way we've connected the filter. And of course, besides this filter, it is also the way we have wound the transformer windings. For example, in this case of a flyback transformer, the dot polarity of the two windings are the opposite. So if the dot polarity is on the upper terminal, in the case of the primary, in the secondary, the dot polarity is in the lower terminal. So which is why when the primary is being energized, the induced EMF produced in the secondary is such that the positive terminal is at the other dot. And therefore, there is no current supplied to the load because the diode is reverse biased, right? Now, this is a very, very neat topology which makes a flyback converter very attractive for many applications. However, there are a few disadvantages of the transformer as well. For example, this entire transformer, when the switch is turned on, it is the primary which is energized by the DC supply, right? Therefore, there is a possibility that this current that is flowing to the primary may be quite high. And in order to be able to reduce this current and also to ensure that this magnetic field which is stored in the transformer is regulated, there is sometimes an air gap placed in the transformer. This air gap is placed so as to increase the magnetizing inductance of the transformer, right? Now, because there is more air gap, the transformer can be a bit inefficient as opposed to a regular transformer because we have additionally deliberately increased the magnetizing inductance. Now, in addition to that, as we've already seen, this dot polarity here ensures that only one winding is energized at a time. And this way, the continuity of supply, or rather the continuity of current flow, is maintained in the transformer. When the switch is turned off, that is when the secondary supplies the load, right? Now, if we were to go back to our original topology, that is, if we bring the dot polarity back to that upper terminal, we have seen that when the switch is turned on, the input supplies the load. So current flows through the transformer all the way to the load. However, when the switch is turned off, there is nowhere for the energy stored in the transformer to go. And this is one of the major reasons why the dot polarity is reversed for a flyback. So now the question is, if we want to go back to the usual topology, that is, if we want to make sure that the dot polarity is at the upper terminal for both windings, what are we to do? In that case, we have to figure out some way in which the energy stored in this magnetic field has some way to dissipate. Because remember, the energy has to go somewhere. It cannot just be broken, right? So now, the only way to do it is by connecting a third winding, right? So we can, however, bring back the dot polarity to the upper terminals, but in order to ensure that the magnetic field is being dissipated, there has to be another path for the for the magnetizing current to flow when the switch is turned off. Because when the switch is turned off, otherwise both the primary and the secondary will be disconnected. And that's not acceptable, because then the current through the transformer cannot completely drop to zero instantly. That's not a good idea. So this is the concept of the forward converter, right? In the forward converter, we bring the dot polarity of the secondary back to the upper terminal, and instead we connect a third winding, which then allows us to dissipate the energy stored in the magnetic field. Alright. So with this, I'm going to end this lecture here, and in the next lecture we will start building the circuit for this converter, which is called as the forward converter. And the reason for the name is pretty simple, because it actually is a complete forward topology where the energy is supplied in the forward direction. That is, when the switch is turned on, the energy completely moves from the source all the way to the load, right? So it's like energy being flowed in the forward direction, as opposed to this topology of a flyback, where energy is being flown back. Energy is being stored in one cycle and being flown back in the next cycle, right? So this is what we'll do in the next lecture. So as before, if you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week, where we'll continue with this topology. So thank you so much for watching, and see you soon. Goodbye for now.